Hello, welcome back. So, we have now completed what I view as the main content of Chapter 1. So what do I mean by that? So we finished Section 1.3, and if you were taking a course with me on proofs, then the very next lecture I would give you is on the start of Chapter 2. So that said, there are many pages between the end of Section 1.3 and the start of Chapter 2. There are many pages in the book. But that's just not stuff that would come into my lectures directly, like here's a lecture on those pages. That said, I want to tell you what's in there. Maybe you'll be interested to know about it. So for starters, there is another section. It's a whole extra section. It's called Section 1.4. The title of it is Bonus Examples. And I'll tell you the same thing that I would tell my own students. What I would tell them is, you are a student of math. You are trying to become a mathematician. So what does that mean? Well, I would say the best attempt to become a mathematician would include reading math outside of class time. Okay, math that is not connected to your lectures directly, that's not things that's going to appear on the test, but math that if you read it, it's going to help round out your education, round out your understanding of the topic that you're studying, or maybe other topics as well. So, it's time for you to try to sort of take ownership of your education and do some things outside of class which help you as a budding mathematician. So Section 1.4 is sort of based on that idea. So at the end of every chapter, the last section of each chapter is called Bonus Examples. And in it, I give you some examples. I counted it up. There are 27 bonus examples divided between the 9 chapters. So you get an average of 3. So on average, you'll get 3 extra examples per chapter related to the topics of that chapter, but they're a little different. They might explore a new topic. So I might build up a little bit of theory or something, and then give you an example related to the topic that also connects to this new theory. Or it might just be they run the full gamut. There might be something it might just be like a harder example, or something more subtle, a subtler point to make. There are many things, but certainly one characteristic is in many of the chapters, I introduce some new topic for at least one of the bonus examples. So you can learn about how other math connects to the topics that you're learning about in that chapter. Okay, so I strongly encourage you, outside of your class time, to be reading other math. It could be another book on the same topic. It could be something else entirely. You could be watching videos to learn about things, like lectures and stuff on YouTube or elsewhere. That's all good stuff. I encourage you to do that. It's a really good way to expand, right? I mean, so much of coursework is they have a goal in mind. You taking a certain class and they say, okay, by week 15, we want the students to be able to master this thing. And it's a pretty linear path. If you want to get all the way there, usually they design the course so it's a little bit of a reach to get there. It's a pretty linear, you have to do this, and it's just the ladder to get to the destination. But expanding your horizons a little bit is very good to sort of, yeah. So so that's my belief. I think you should do it. And I thought I would just take a moment. I'm going to switch on the camera so that way you can see an actual copy of the book and you can see what's in there. Okay, one sec. Okay, so this is the book. If you open it up, this is the end of Section 1.3. So this is the problem that we did in the last video where you have the numbers between 1 and 200 and you want to pick 101 of them so that one and then you want to guarantee that one always divides another one within your set. Anyway, so these are the boxes. If you remember that one, you can kind of see the numbers that would be in these boxes. Anyways, so that's the end of that problem. And you can see there's a little bit of wrap up. And then we have Section 1.4, bonus examples. And I start just like with the monologue I just gave. It is important that students take time to read and digest additional proofs beyond the ones covered in class, blah, blah, blah. And then I get into the actual bonus examples for this chapter. And you can tell, so this is where I'm starting the pre-work to lead up to the first bonus example. And this is where I start the first bonus example. So this is an 8.5 by 11 page. These are relatively big pages. So it's, you know, a lot of buildup. So what I'm doing is I'm discussing what a graph is. So there's a type of math called graph theory. This is not like y equals x squared in the xy plane, not those types of graphs. I'm talking about there's vertices and edges connecting the vertices, and those vertices have degrees. So I don't know, I was just doing a quick review of what the basics of graph theory are. And then I give you this first bonus example. It says, suppose G is a graph with at least 2 vertices. Then G contains 2 vertices which have the same degree, which means the same number of edges touching them. So that's always the case. Every graph with at least 2 vertices, you can always find 2 vertices in your graph which have exactly the same number of edges touching them, which is kind of interesting. And it's a good problem because, you know, it's one of these problems that, so when you figure out what are my boxes, what are my objects, you discover that you have the exact same number of objects as boxes. And the pigeonhole principle doesn't apply then. For the pigeonhole principle, you need more objects than boxes. So, you know, you kind of are caught in a bind where you said, okay, I have the same number of objects as boxes, but I still want to use the pigeonhole principle. How do I get around it? It's a very nice little problem. So if you want to, you could read that on your own. And then that's the proof. So 3 pages to do this first bonus example. And this next one I really enjoy. I'll show you this one. So if you draw 5 points on the surface of an orange in marker, so an orange, I mean like a real orange, something like this, then there is always a way to cut the orange in half so that 4 of those points, or some part of each of those points, all lie on one of the halves. Okay, so this is pretty amazing. It says, let me just show it to you a little bit. If you take an orange, or in this case, a mandarin orange, sometimes known as a cutie. So I went to my grocery store and they didn't have oranges. They said that oranges are out of season. So they only sell these smaller versions. So I got these smaller versions. Anyways, if you take a marker and you write dots on an orange, 5 dots. So I had my toddler draw these dots. Only thing is I gave him the advice, if he draws them too close to each other, then it's easier for me. So I told him to space him out as much as possible, and you can see he did a pretty good job. Actually, very good job. Good job, kiddo. So there's always going to be a way that I can take a knife, angle the orange in some direction, cut the orange into 2 equal halves. So imagine it's like a sphere. So it has to go through the center of the sphere. It has to be really the 2 halves are equal. I can't just cut off a little tiny end. It has to be right through the middle. And on one of the 2 halves, after I cut it, I can show you one of the 2 halves, and 4 of the dots are there. And that seems surprising. How could you get 4? Shouldn't 3 be the number? And indeed, the general form of the pigeonhole principle only gives you 3. 3 out of 5 can be in 1/2, but how do you get 4? It's a little tricky, but there's always a way to do it. So I've done this exercise in class. I brought a bunch of oranges. I've tossed them out to students, handed out markers, and, you know, 5 students did their very best to put dots in places where I couldn't find a way to cut it in half and get 4 of the 5 on 1/2. But except for a couple of times I make a mistake, but basically every time I can get it. Now in the theorem, I did say that sometimes it's going to happen that I will accidentally cut through a dot. And in those cases, you have to give it to me. You have to say, okay, so the dot is on both halves. So either half I pick will have that dot. Now, it rarely requires that. 9 times out of 10, I don't need to do that, but occasionally it happens. Okay, that said, let me now look at this and see if I can figure out a way to do it. Okay, yeah, I think, where's that one? Okay, I think this will do it. So if I cut, it's kind of pointy on the bottom there. I think just about there Should do it. Okay. So I have the 2 halves. And yeah, this one is slightly smaller. I guess I didn't go exactly, but it's pretty close. And you can tell, let's see, I got 1 dot, 2 dots, 3 dots, and oh. So I actually did cut this one in half. Okay, well, you got to give it to me. That's the rule. So you can see 1, 2, 3, and 4. Let's try another one. Let's see if I can get this next one a little bit better. So my toddler also did this one. So I have 1, 2, 3, 4, 5. Guess I should have practiced a little bit. Okay, pretty sure this should do it. So if I angle it just like this and cut right through the middle. Okay, those are the 2 halves. And I believe we have 1, 2, 3, 4. Okay, so that was a good one. Got all 4. And if anything, the half with the 4 might have even been slightly smaller. So if anything, I could have been a little bit more generous. And so even on the very slightly smaller half, I have all 4 appearing. So there you go. That is the cool rule. I brought 2 more mandarin oranges. I thought I'd do a couple demonstrations for you. So I'm not going to be thinking too hard about this. 3, 4, 5. Okay, let's see how hard I made it on myself. I actually left a pretty big area over here, so that's helpful. Or is it? Yeah, it should be. Yeah, okay. So if I just cut right through the middle, let's see. 1, 2, 3, 4. So there's an old theorem from geometry that's helpful when proving this. So you can see 1, 2, 3, 4. And you can take a look at the book. 1, 2, 3, 4. How would I make it hard? Can we find the biggest space? Put a dot there, maybe right there. Okay, 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. Let's see here. How do I do this? I did make it tough on me. I think I'm going to cut that one in half if I do it. I have a lot of that are kind of linear with each other, which is kind of a problem. Okay. Let me just see if this works. Okay, yeah, those are pretty equal. Did I do it? Ooh, just got that one. 1, 2, 3, and 4. You can see they're kind of faded, but on this half, you can tell there's only 1. So, only 1 there. 1, 2, 3, and 4. Okay, so there you go. That's an exhibit of this problem. And that was the second bonus problem in this chapter. All right, folks, that's it for today. If that sparked your interest, go and get yourself a copy of the book. It's a good book. So that's it for bonus examples, but we're not quite done with chapter 1 yet. Next time, we'll talk about pro tips. We'll talk about an open question. And we'll talk about exercises. So come back next time. We'll officially wrap up chapter 1 And after that, we'll start chapter 2. All right. See you then.